Hello and welcome to another Matt video, this time going through Matt 2019 question 2. A YouTube commenter, M27, I don't know exactly the rest of it, it was kind of like a jumble of letters and numbers, his username, but he requested it and I glanced at it and thought, yeah, I remember doing this, like I can't remember when I probably answered it in 2019 or 2020 on holiday, like, or, no, summer holiday basically, after it was, yeah, 2020 summer holiday, something like that, but it was a while back, and I glanced at it and I thought, yeah, I remember this, and I remember liking some of it, as in enjoying lots of it, but also finding part three, weirdly enough, this little sentence here just kind of got the better of me. I think I've got a lovely answer to part five though, which is different to the mark scheme, and I fully invite you to criticise it, because sometimes, when I come up with these funny ideas, and not necessarily, people are quick to, as they should be, to discuss and criticise it. But I think I've got a lovely answer to part five, and we'll see if you believe me. Okay, so anyway. What we're doing here, we're multiplying out this horrendous multiplication of brackets all the way up to x to the k, and you can see the pattern's not difficult, and the first thing they're asking for is, what's the degree of this polynomial? Yeah. Now, if you want to work out the highest power over here, then we're going to have to add up, basically what we're going to have to do, and I've tried to put a little 1 in on that x there, what we're going to have to do is obviously the highest power over here is obtained by doing x times x squared times x cubed all the way up to x to the k. So in other words, I'm going to write down first, well, x to the n equals x to the 1 times x to the 2 times all the way up to x to the k. In other words, n equals the sum of the numbers from 1 to k. Now you should know this off by heart for the next exam, that is just k times k plus 1 over 2, because that is triangle numbers, or the sum of the integers. It is absolutely the sum of r from 1 to n, if you've done that chapter in further maths. It's also an arithmetic sequence, so you could have a is 1, d is 1, and use Sn equals n over 2. In this case, sk equals k over 2. 2a plus n minus 1d, so 2a plus k minus 1 times 1. And that should give you the same answer. Look at that, we get 2 minus 1, so we're going to get k plus 1 times k over 2. We get exactly the same thing. Or you can look at it and prove it like Gauss did it, or you can just think this is just a formula for triangle numbers, it's just k plus 1 over 2. Okay, so you need to know that formula, definitely. That is one you should be really aware of. You could even treat it as a quadratic sequence, how about that? Because it is a quadratic sequence. So anyway, we've got that, and it just said write down, so we don't even need to do any proof. Okay, part 2 is where it gets tougher. By setting x equals 1 or otherwise, explain why a max is greater than or equal to 2 to the k over n plus 1. So I did as I was told. Yeah, I didn't use the or otherwise. I did as I was told, and I noticed that pk of 1 is going to be equal to, well, that's going to be 2 times 2 times 2 k times, yeah? And I also plugged it in on the right hand side, and I ended up with a0 plus a1 plus a all the way up to am. So we now know the sum of the coefficients. It equals 2 to the k. So I thought, okay, that's interesting, lovely. How can I link this to a max? Well, upon looking at it again, like this was just when I glanced at it, I thought, and I didn't have this way written down when I had originally answered this question, but I thought, well, surely a max, one of the things you can say about a max, I saw this over n plus 1, and I thought, how many terms are there? There's n plus 1 terms, yeah? I could say the average coefficient, yeah? Oh, why am I using modulus for average? What am I doing? I could say the average coefficient is going to be equal to a0 plus a1 all the way up to an divided by n plus 1, yeah? That's definitely true, isn't it? The average is just add up the numbers and divide by the number of numbers. And if you've ever got an average, and you compare it to the maximum value in a list, surely the maximum value is always greater than the average. So a max must be greater than or equal to the average in the list, yeah, because you know what I mean. How can the average possibly be greater than the greatest value in the list? It doesn't make any sense. That you can have the average equal to the greatest number in the list if all the numbers in the list are the same: 5, 5, 5, and 5. The average will be 5 in that list, and the maximum value is 5. But otherwise, the maximum value in the list must be strictly greater than, well, or equal to, as I pointed out here, a bar. So what we have straight away then is a max is greater than or equal to a0 plus a1 plus all the way up to an over n plus 1, and then we have the result, because from substituting in x equals 1 we can see that this is true, that the sum of the coefficients is 2 to the k, and so we've got it. So that's directly because, and I might even write in some words to explain this, the mean in a list of data is less than or equal to the maximum value in that list. And I hope they didn't want me to prove that, because is it not just absolutely obvious? So that's what I used for this one. I think when I did it before, just glancing down my notes, when I'd done it before, I just simply pointed out that yeah, because the coefficients are always 1 or greater, then you're going to have a max times n plus 1 in brackets is greater than or equal to the sum of these values, just because, you know, each one of these, you know, the maximum this adds up to, well, the minimum, sorry, this adds up to is n plus 1, so you can rewrite that as an inequality. So there are other ways of doing it, yeah, but I'm just going to use the idea that the maximum value in a list is going to be greater than or equal to the average value, and then that gets me it nicely. Okay, part 3. This was one of most, I just think they put this in quite an abstract way. When you realise what they want, it's obvious, isn't it always the case in retrospect? But yeah, they're saying this curious fix I is greater than or equal to 0. So I is a constant, but it's greater than or equal to 0. Yeah. Explain why the value of AI eventually becomes constant as k increases. Well, as k increases, we've got more brackets here. Yeah. So let's fix AI. Well, let's fix I as equal to 2. Yeah. Now let's think about how this works. Yeah, and then let k equal 3. We're just going to like investigate this. Find 1 plus x times, let's just do k equals 2, 1 plus x squared. When we do that, we get 1 plus x squared plus x cubed. Yeah, lovely. Yeah, so clearly here you can see that a2 is equal to 1. Yeah, now a2 will remain constant as k, you know, as in equal to 1, as k increases, because of the way these multiplying out brackets works. Yeah, because for k equals 3, yeah, all we're going to do is this 1 plus x squared plus x cubed, and we're going to be multiplying that by 1 plus x cubed. Yeah. Okay, so why is it that a2 stays as 1? Well, it's because you're going to times it all by 1 first. Yeah, and then you're going to times it all by x cubed plus x to the 4 plus x to the 5 plus x to the 6. Yeah, in other words, the only constants which are going to change are not a0 or a1 or a2 or even a3. Yeah, the constants which are going to change, sorry, a3 does change, I apologise, because that suddenly becomes 2x cubed now, and an x to the 4, x to the 5, x to the 6. So the only constants which can change are those constants which are greater than or equal to k. Yeah, so you can kind of see it now from this. Now, I was quite careful the way I described this in my notes, so I wanted to make sure I got the marks, if you see what I mean. Like, so I'm just going to slightly change that. This was just in my like kind of investigation. I was investigating the algebra, because for k equals 3, we will multiply this by 1, and then x cubed, which will not change the x squared coefficient. And now we can say, in general, AI is fixed once k is greater than or equal to I. Yeah, once you get to that term beyond, you know, that term where k is equal to I, you start adding on basically more more like more coefficients of x to the n, where or x to the k, basically. It's interesting to see how it multiplies out in the resulting expansion. Basically, you're going to get a higher power basically when you expand that out. Key thing to notice is that that happens once k is greater than or equal to I. Yeah, and that should convince them. So I thought that was quite tricky. Yeah, hard to explain as well. I don't know if I'm going to get the marks for my explanation there. I can see why it works, as often the case, and it's all about communication, isn't it? I'd take a simple example, fix I equal to 2, work out that what the coefficient of A2 is, it's equal to 1, and then I'd start multiplying out for k equal to 3 and realise, oh yeah, A0, A1 and A2 aren't going to change, it's only A3 which might change. Okay, a student correctly calculates k equals 6 and multiplies all this out. Wow! On the basis of this calculation, the student guesses that ai equals am minus I. This immediately reminds me of n choose r equals n choose m minus r, and I strongly encourage you to prove that with binomial expansions. It's not with the formula for n choose r with the factorials in it. It takes seconds, but try and prove that formula for me, because it immediately reminded me of the symmetry in Pascal's triangle. Okay, by substituting x to the power of minus 1 for x, or otherwise show that the student's guess is correct. I took the suggestion, the suggested approach, and it popped out really quite nicely actually. So first thing I did was I plugged in x to the minus 1 instead of x in there. So pk of x to the minus 1 equals, okay, what have we got? 1 plus 1 over x now, and then 1 plus 1 over x squared, dot dot dot, all the way up to 1 plus 1 over x to the power of k. Cool. Now do it on the other side. You're going to have, now here, remember we're plugging in x as 1 over x, so you've got a0 plus a1 over x plus a2 over x squared, yeah, plus all the way up to an over x to the n, yeah. Now, what I thought immediately was, this is crying out for both sides to be multiplied by x to the n. Yeah, just because I really want to tidy up the right hand side. The right hand side then becomes a0 x to the n plus a1 x to the n minus 1 plus dot 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 dot, and then you're going to have plus an minus 1 x plus an. Yeah. So basically the coefficients are now backwards, yeah, which I thought was exactly what I should be looking for. Now, in order to times this side by x to the n, I reminded myself what I wrote down in part 1, which is that n equals kk plus 1 over 2. Yeah, you really kind of need that here. So if we're timesing by x to the kk plus 1 over 2, remember that kk plus 1 over 2 is actually the sum from 1 to k. It's exactly the same as timesing by x to the 1 times x to the 2 times all the way up to x to the k. Yeah. Hence, we can times one of those x's in that bracket, giving me x plus 1. We can times an x squared into this bracket, giving me x squared plus 1. We can continue this all the way up to the last one, where we're going to times it by x to the k, giving me x to the k plus 1, and we have this lovely setup. Now, this is equal to pk of x. Thus, the left-hand side is, yeah, pk of x equals a0 xn, yeah, plus a1 xn minus 1, yeah, plus dot dot dot, plus am minus 1 x plus an. But we already knew by definition that it equaled a0 plus a1x plus dot 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 all the way up to x an x to the n. Yeah, this is just the coefficients written in the reverse order of this one, and that can only be true, this can only hold if ai equals a of n minus I. Yeah, can only be true if that's the case for all I. Cool. Okay, right, so that's lovely. Lovely. Now, what we got? Part 5. Okay, this bit, yeah. I think this bit would definitely stress people out. I think looking at the answer in the mark scheme, that probably stress people out. So I'm going to try and make it a little bit nice. I'm going to show you what I did. I quite like this, yeah. On the basis of the same calculation, the student guesses that all the whole numbers in a range, 1, 2, up to A max, appear amongst the coefficients. What they're saying is, whatever the largest number is, in this case 5, all the numbers, natural numbers, appear from 1 up to 5, yeah. Interesting supposition, yeah? You know, you're eventually going to get all the numbers in there as k gets larger and larger. It's going to produce all the natural numbers forwards and backwards. Some of them might be repeats. It's not saying some of them aren't repeats, but all of them should appear, yeah? Now, it says use part 2. This thing here, A max, which is apparently greater than or equal to 2 to the k over n plus 1. Yeah, to prove that a student's guess is wrong. Justify your answer. Now, I've done it differently to them. I started by looking for a counter example. I really did. I took a guess. I guessed basically because I thought this must grow really large 2 to the k, and now I'm definitely going to use this result as well. Yeah. Now this result is telling us that it goes forwards and then backwards in exact, and it's symmetrical. The coefficients are symmetrical. That's what that result is telling us. The coefficients must be symmetrical. So my thinking was this. Yeah. For a certain value of n, let's say n equals 10. Yeah. Then if the numbers read the same forwards as backwards, then, at the most you could have 1, 2, 3, 4 and 5 here. Well, let's say your A max in this was like greater than or equal to 8. Yeah, that wouldn't make any sense because you can't have all the natural numbers from 1 up to 5, all 8 natural numbers listed when you've only got 5 coefficients. Do you see what I mean? You must be missing some numbers. That's the principle I was using. I first guessed that k equals 7. I said guessed and I said try k equals 7. Yeah. And then I noticed that we had, okay, A max is greater than or equal to 2 to the 7, what is that, 128 over n plus 1. Now remember, n equals k plus 1 over 2. Yeah, so if we can just work that out, what we got, 7 times 8 is 56, divided by 2 is 28. Yeah, and so that's 29. And so 2 to the 7 is 128 over 29. What is this? Basically 30, 60, 90, 120. It's greater than or equal to 4. Yeah. Now that's no good, 4-ish, 4 and a bit. Yeah, I'm just trying to show you my reasoning here. I didn't write this down, but I did initially guess at 7, but so I scribbled some stuff down. But that's not good enough, yeah, because we've got 28 terms in this expression, yeah, in the right-hand side after you've multiplied it out, and therefore you're allowed to have up to 14 numbers here, and we just know that A max is greater than or equal to 4. Yeah, that's no good. So I now tried a new guess. I went, okay, let's try and find a counter example with k equals 12. My thinking was I just need to get the top big enough because 2 to the power of is going to grow really quick. Okay, we end up with A max is greater than or equal to, by the way, k equals 12, then n is going to be equal to 12 times 13 over 2, which is 6 times 13, so 78. Yeah. Okay, so A max is going to be greater than or equal to 2 to the power of 12, and I was hoping that this would work before I run out of my powers of 2, over n plus 1. Well, that's 79. Yeah. Okay, so we've got 2 to the power of 12 over 79. Obviously, this is a non-calculator paper. Now, I know that this is 4096 over 79, yeah? Now, if it's greater than or equal to that, then it's going to be, we better work out what 4096 divided by 79 is. Okay, what do we get with 4096 divided by 79? Well, let's actually do it like this. 4096 over 79. Okay, and we're worried about A max. You can do it sort of roughly, but let's just get the first decimal place right. Okay, so time for a bit of old school long division. Okay, 79's into 409. We're going to have 320, 400. 5 times 79 is going to be like 5 times 8 is 400. Take away a 5, you get 395. So this goes 5 times. Remainder, 395 to 409 is 14. So then we're going to have to do 79s into 146. It doesn't even go twice. There is quite a remainder here. 21 plus 46, 67. Okay. I'm now basically at the point where I can say it basically goes just under 53 times, yeah? Cool. That goes something like 8 times, I think, looking at that. But I'll just stop there, yeah? I've got enough accuracy now, yeah? Because I know that for k equals 12, A max must be greater than or equal to quite a big number, 51.8, yeah? In other words, A max is greater than or equal to 52. Now, it is impossible for all 52 numbers to be there, yeah? Remember, A max, the biggest one, is 52. It's got to be bigger than 52, in fact. It's 52 or bigger, yeah? So that's the biggest coefficient in this list. But look back, and n is 78, and it reads forwards the same as backwards. So now I just need to point out, but the first 39 coefficients that lead up to A max cannot include the first 52 integers, yeah? All of the first 52 integers, or, natural numbers. Hence, you cannot, you will not get all the natural numbers listed in order. Looks like it's gonna work, but when you actually see that, it's not going to work, is it? So I hope you understand my argument. I hope my argument's clear for the examiner to understand, more importantly. I've just basically looked for a counterexample which demonstrates that the maximum coefficient is so large that you couldn't have possibly all the numbers represented, even if you had 1 only appearing once, 2 only appearing once, 3 only appearing once. That's my argument. Because there's 79 numbers, because there's actually n plus 1 coefficients, because there's 78 of them, if you halve that, you've got 39 numbers leading up to A max, and in those 39 numbers there's no way you can have all 52 integers represented. Please let me know what you think of my argument, and if you don't like it or do like it, I'd love to hear. All the best, and bye bye. Good luck in the map, by the way.